In the earlier classes, we had seen about roles of various R groups. And we had also seen that R group of histidine, imidazole group, this is the only one which can act as a buffer at the physiological pH. It's a very narrow range of pH 7.4. Actually ranges from 7.35 to 7.45. So I thought of making this again, although there may be some repetition, because this is the point where I have seen that the students are making maximum mistakes. They say that an amino acid acts as a buffer at the isoelectric pH. So there is a lot of confusion. To the best of my understanding, I will try to clarify some of this. And we had also seen that amino acids are amphoteric. We had also seen acid-base properties of the amino acids in the previous class. Now let us see what is an acid, what is a base, what is a buffer in a more elaborate manner. Acid, abbreviated as HA, it's a proton donor. You can see here H, I think it's concealed, plus A minus. So it is a proton donor HA, so this is called a acid. Now, if it is a reversible reaction, you can see that A minus is accepting a proton and giving rise to HA. So proton acceptor is a base. And these two together, HA and A minus, they are called conjugate acid-base pair. What is a buffer? Every word is important. Buffer resists change in the pH when a small amount of acid or base is added. Please note these two terms. Number one, resist. It does not prevent. Second, small amount. When small amount in our blood, small amount of acid, bases during metabolic processes, they are generated and they tend to change the pH. So buffers, they resist change in the pH. And there, in this class, we are going to study role of histidine. Histidine is very prominent, very abundant in hemoglobin, which is an important buffer among others. So buffer and acid and its conjugate base, they together act as a buffer. And a buffer is most effective when acid and conjugate base are present in equimolar concentration. HA की concentration nearly equal to A minus concentration. That time buffer is most effective and an important relation exists. pH is equal to pK. As you know that every acid has got a characteristic pK value. Every dissociable group has got. So we will have to examine this part in slightly more detail and then we will return. So I'm sorry. We'll have to see Henderson-Hasselbalch equation to understand that concept. We said that when A minus and H plus, they are equimolar concentration, then the buffer is most effective. So, अगर ये दोनों equal है, this ratio becomes equal to 1. So now the relation changes, the equation changes to pH is equal to pK plus log 1. And log 1, as you know, it is equal to 0. So now pH is equal to pK plus 0. That means pH is equal to pK. So a buffer is most effective when two relations exist. Number one, acid and base concentrations are equal. And number two, when pH is equal to pK. I'm sorry, some confusion. So I return to the slide which I had shown in the last lecture with some difference. amino acid can exist in three charged states: cation, positive form, Zwitter ion, abbreviated as Z, neutral, and the negative form, the anionic form. Now, at a very low pH, at a lower pH, relatively lower pH, the amino acid would exist in the cationic state. And this is the form, cationic state. And as you increase the pH, for example, by titration with NaOH. Now we are considering a typical amino acid, for example, alanine. तो alanine में solution में low pH पर ये है. When you increase the pH gradually, it will be gradually carboxyl group will be donating, liberating it H plus, and this form called Zwitter ion will be formed after liberation of the H plus. Now Zwitter ion, you can see it is neutral form. Further titration with NaOH, further increase in the pH will give rise to the anionic form. So these are the three charge states of amino acid we had seen earlier. Now we are going to examine from a different perspective now. Just consider till here, yahan tak. Is cation not acting as a proton donor? So it is an acid. Zwitter ion, it's a conjugate base. Proton donor acid and conjugate base after liberation of proton. This is Zwitter ion is the conjugate base. So buffer is most effective when cation acid or base की concentration equimolar है. So it will act as a buffer when concentration of cationic form and the Zwitter ion form are equal. I'm going in the opposite way now. Buffer ये act करेगा when these two forms, somewhere in the middle of the titration, these two forms will be in nearly equimolar concentration and it will be acting as an effective buffer. और PK, PK कितना है? Dissociation of COOH हो रहा है ना? तो PK of COOH is, let me see, it is 2.39, I think. 2.39 or 2.34, I think. Yeah, 2.34 hai. So it will be acting as a buffer. An amino acid will be acting as a buffer at pH of 2.34. And this corresponds to dissociation of the carboxylate group. But will it be of any use in our body? No, because body pH is far removed, 7.4. अब इसको आप देखो, सेकंड फेज को आप देखते हैं. Here, Zwitter ion is acting as an proton donor, therefore acid, anion a conjugate base. So, middle of the titration somewhere, when the concentration of acid and base will be equimolar, it will be acting as a buffer. और pK कितना है pK का? Because this is corresponding to dissociation of the amino group. और amino group का जो pK है 9.69. Again, far removed from the physiological pH, so it will not act as a buffer at the physiological pH. So, alanine cannot act as buffer at the physiological pH within our body. It can act as a buffer at these two, but that is of no use as buffer within our body. What is so special about imidazole? Let me revise. Alanine has got two buffering zones. First to dissociation of carboxylate, second to amino group. So what is special about imidazole group of histidine? It is a dissociable group. So imidazole group is capable of donating a proton, in the process getting converted to its conjugate base. So therefore, it will have a third buffering zone also by the same logic which we have examined in detail. At what pH? At pK of the imidazole group, at pK of the dissociable imidazole group. It is given at some places as 6.8, 7.1. That is understandable because within proteins, actually, pK value that can show fluctuation. So both are, if you see 6.8 to 7.1, it is quite near physiological pH of 7.4. So histidine is able to act as buffer at the physiological pH. And histidine is very abundant in hemoglobin. So hemoglobin is an effective buffer in our body. A question for you, which are the other extracellular buffers and intracellular buffers? Find out. So we had seen earlier PI, isoelectric pH. Now let us see fallacy of the answer. Ki every amino acid acts as a buffer at the isoelectric pH. ये देखिए isoelectric pH पर तो when the zwitter ion form predominates, you can find addition of NaOH is causing a sharper rise in the pH. So it is not acting as a buffer. Rather, it has got least buffering capacity at the isoelectric pH. Buffering capacity when pK of carboxylate group, pK of the amino group, and in case of histidine, a third pK of the imidazole group, which is very close to the physiological pH. So this, I think I would not repeat. Each amino acid, zwitter ion at its isoelectric pH, यहाँ buffering नहीं होती है. Buffering zones होती हैं. One corresponds to dissociation of carboxylate, another to amino. And finally, let me repeat, pK value of imidazole group of histidine is relatively closer to physiological pH. So therefore, it is capable of acting as a buffer at the physiological pH. Thank you so much.